Does it feel like hot in here to you guys too? Because I know it is to me. Why? Because today we're working on acids. And nothing is hotter than getting your skin burned off with hydrochloric acid. Not like hotter as in hotter, but like hotter as in literally your skin's burning off. Okay, so acids and bases. I mean, the thing is, acids get all the hype. And people say, oh, acids cool or getting burned with acids. Bases are just as cool/dangerous. So we're going to be treating them both equally in this video because we believe in equal treatment of acids and bases. So that being said, first things first, we're going to start our equal treatment with totally ignoring bases and talking about what acids do in reactions with metals. So let's say you have the acid, and we're going to go to our classic favorite acid. It's the best, hydrochloric acid. You know, it's stomach acid. It's the acid you go to when you want acid. And we're going to combine that with a metal, let's say aluminum. So when you take that plus aluminum, so you have your hydrochloric acid, HCl, plus aluminum, Al, it's going to then produce a salt and hydrogen. A salt is just an ionic formula unit. It's just a fancy way of saying that. For example, you know, you guys should be familiar with the famous salt, NaCl, but this is just one form of salt. In this case, we're getting an ever metallic salt, and you're getting that AlCl3. So what you get is you have your HCl plus Al will give you an AlCl3 plus hydrogen. Hydrogen's just doing its thing. Because it's a single replacement reaction, which you guys are probably familiar with from last year, or the year before last year, depending on when you're watching this video. And you should know, single replacement reaction, all it's doing is it's saying that on the activity series, aluminum has more cachet, so it bumps off the hydrogen, takes its place, combines with the chlorine, and then the aluminum and the chlorine go off and do their thing as a salt, and the hydrogen goes off and bubbles off as a gas. That's all it is. So that's what happens when you combine an acid and a metal. It's going to create a salt, which is an ionic formula unit, and hydrogen. However, what happens if you combine an acid and a base? Well, what happens when you combine an acid and a base, assuming that the acid and the base are in correct quantities, is that it neutralizes. I'm not going to make that analogy right now, but so an acid and a base, you combine it, and then we'll take another two common acids, NaOH, sodium hydroxide, and we'll combine it with the acid, I guess hydrobromic acid, and that's going to give us, well, you have your sodium hydroxide, and what happens is when you combine the acid and the base, is that you're going to get a salt, again, that ionic formula unit, plus water. Because the H, the hydrogen, is going to combine with the hydroxide ion to form H2O. So what you end up getting is going to be, you have bromide from the hydrobromic acid, and then you also have sodium from the sodium hydroxide, so you're going to get sodium bromide, which is going to be your salt. And then you're going to get, in addition to that, straight up H2O, water. Okay, so that covers it for an acid and a base. So now we know what happens when you combine acid with a metal. Boom, you know you get that hydrogen with a salt. When you combine an acid and a base, you get water and a salt. However, what about when you combine acid and a carbonate? Okay, we're going to take a step back here for a second, just to make sure you're comfortable with what a carbonate is. It's pretty straightforward. A carbonate is whenever you have something with carbon, and in particular, carbonate. You guys are familiar with the ion carbonate, CO3, and that's all it means, is that it has CO3 in it. So if you're dealing with something that has CO3 in it, then it's going to be a carbonate. So what happens if you combine an acid with a carbonate? We're going to take the example of hydrochloric acid again, because it's our favorite, and calcium carbonate. So with hydrochloric acid and calcium carbonate, what you end up getting is, you guessed it, what's the first product, guys? Salt. They all make salts. Just if you have an acid or a base doing something, you're probably going to end up with a salt on the side, which is your ionic formula unit. However, it's also going to create water, so it's like a neutralization reaction on steroids, and on top of that, it's going to create bubbles. Bubbles in the form of carbon dioxide. So for example, you take the reaction hydrochloric acid plus calcium carbonate, and it's going to create calcium chloride, which is going to be your salt in aqueous form because it's still floating around there in the solution, plus liquid, which is going to be your water, H2O, and then finally CO2, your carbon dioxide. Pretty straightforward. And if you look at the formula, you can see kind of where it comes from. The carbonate loses an oxygen to become carbonite. Well, yeah, it loses an oxygen, doesn't become carbonite, because that brings it down to CO2, carbon dioxide. The carbonate loses the oxygen and gives that oxygen over to the hydrogens from the hydrochloric acid. Then that creates water. By the carbonate losing an oxygen, it creates CO2, carbon dioxide, and now the the chloride is going to be free to combine with the the calcium, to then create the new salt, which you could also look at it as being the anion of the acid and the cation of the base combine, and they form the salt. Boom, there we go, that's our reactions. So let's review it real quick. What happens when you combine an acid with a metal? You get a salt and hydrogen. What happens when you combine an acid and a base? You get a salt and water. What happens when you combine acid and a carbonate? You get a salt and water and CO2, carbon dioxide. Boom. So that being said, that allows us to move on. So we have acids and bases. Acids do their acid thing, bases do their bases thing. But how do we know the difference between an acid and a base? Because if the acid and the base are both the same pH scale, and we'll talk about that later, but they both have the same amount of reactivity, you're not going to be able to test the difference between acid and base by pouring it on your skin, obviously, because they'll both burn your skin off. And it's kind of hard to tell the difference between getting your skin burned off and getting your skin burned off. So we need a slightly more nuanced manner in which to figure out how to determine acids from bases. You're in luck because we have indicators. Indicators are simply chemicals that you can pour into an acid or pour into a base, and they say, okay, I am now in an acid or in a base, and I'm going to turn a certain color. They're really, really simple. In general, acids will turn a pinkish red hue. In fact, almost always will turn a pinkish red hue. Bases will turn somewhere in the blue spectrum, blue to purple. And keep in mind, indicators are limited because while there are universal indicators which work over a wide scale of pHs, the majority of indicators only take up a small piece of the scale. Which is to say, an indicator that can tell you that hydrochloric acid, how acidic hydrochloric acid is, won't be able to tell you how acidic a weaker acid might be. Say maybe hydrosulfuric acid. Or just sulfuric acid, no hydro needed. Same thing for bases. So when you're using indicators, you have to carefully select your indicators depending on what situation you're in to make sure that you have the correct indicator. But other than that, it's pretty straightforward. Drop your indicator in. Does it turn blue? It's a base. Does it turn red? It's an acid. Yay. That's it. That's really it. However, there are other useful tricks you can use using indicators. So now we say, we know when an acid stops being an acid or starts being an acid. We know when a base starts being an acid or stops. When a base starts being a base and stops being a base. Because these indicators can tell you when it's basic, when it's not basic. So, what if you were to have a solution with a certain amount of hydrochloric acid in it? Because why? Hydrochloric acid's our favorite. We've told you that before. You have a solution with a bit of hydrochloric acid in, but you don't know how much hydrochloric acid, and you want to find out how much hydrochloric acid. So what do? You use titration. Titration is when you take this really long, skinny burette that has a twister on it, a stopcock, I think is what it's called. And what it does is it has measurements up the side, like it's a giant graduated cylinder. You put it over your solution. So you say you have a solution of HCl. You have your solution of HCl in a nice little Erlenmeyer flask that has a stirring bead in it, so it keeps it stirring around. You take your burette, hold it over it, and you use the stopcock to turn again and again and again in order to release small amounts of what? A base into your acid. Because remember, we learned how you could do a neutralization reaction. So how this works is you have an indicator in said acid, drop a little bit of red cabbage juice, will do the trick. Drop a little bit of red cabbage juice into that HCl solution, and then you have a measured amount of, say, sodium hydroxide, and that sodium hydroxide very conveniently reacts with HCl on a 1-to-1 ratio, so you're using sodium hydroxide. It'll react at a 1-to-1 ratio, and you just drip it in bit by bit until finally the indicator goes from being red, because it's been acidic this whole time, to going back to neutral, or switching over to blue, which would mean that you would have just crossed the line into basic. Shaboom. That's really all it is, and now you know the fact that, hey, your solution just became basic. And that means that at that point, you just got just enough solution in there, just enough sodium hydroxide to neutralize your hydrochloric acid. And at that point, you can go backwards and say, okay, how much sodium hydroxide did I put in? You know it's a 1-to-1 ratio, use stoichiometry, and you can figure out how much hydrochloric acid was present in your solution. And congratulations, because however much hydrochloric acid was present in your solution, hopefully you're done with said solution now, because you aren't using it for anything else, because now it's just a bunch of salt and water. And that being said, we are complete. So once you reach that equivalence point with your titration, you get there and you say, okay, we are now here. Go back, use stoichiometry. You can figure out what's going on. And then for your reactions, we'll go back over those one more time. When you have an acid and a metal, you get a salt and a hydrogen. Just hydrogen. When you have an acid and a base, you get a salt and water. When you have an acid and a carbonate, you get a salt, water, and carbon dioxide. You get the value pack for that one. And then for titration, you just take your burette, drop an amount of base or acid into your solution, which could be acid or basic. Just drop the conjugate, so whatever isn't in there, drop it in. Make sure you know how much you're dropping in. And then you can use stoichiometry after your solution switches from acid to basic and reaches that equivalence point where it's in the middle between them, and that means it's been neutralized. Use stoichiometry to figure out from how much of the base or the acid that you dropped in, how much of the acid or the base was originally in your solution. And there you go. Those are the properties of acids and bases. And remember, we love you just as much as acids and bases. Not really. We prefer hydrochloric acid.